Hello everyone, my name is Anastassiya. I'm originally from Kazakhstan, but I study at a boarding school in Cyprus, which is where I am presenting from today. I worked on this project under the guidance of my mentor Husni. And basically, I chose this topic because I have been always fascinated by astrophysics and how our universe is working. And also, I wanted to work on something that not only inspires me, but also has the potential to contribute to the world. And in this project, I built an AI system to classify astronomical objects efficiently and accurately. Today, I'll be sharing the key ideas and results of my work. Um, so every night, telescopes capture millions of cosmic objects, galaxies, stars, quasars, and others. But who decides what each one is? Traditionally, astronomers or even volunteers. However, with the enormous amount of data we now collect, it's impossible for humans to keep up. And this graph shows how overwhelming manual classification is. The red line referred to total reported events, and blue line reported to events that was confirmed by astronomers. And as you can see, it's very overwhelming, and we need to do something with it. So why does classification matters? Because accurate classification is a foundation for major areas of astronomy. It allows us to trace how stars are born and die, to understand the evolution of the universe, and identify rare and interesting events like supernovae and kilonovae. And without automation, we risk missing some important discoveries. Um, So to train my model, I need to use data. The data set I used is a plastic data set. It was created for the LLST classification challenge, and it contains around 1,200 objects and over 400,000 individual observations overall. And each object in the dataset is observed multiple times, and every observation includes several key features. The MGD, or modified Julian date, records the exact time of observations, which allow us to build a time series or light curve showing how the brightness changes over time. And flux tell us how bright the object appeared, while flux error shows the uncertainty in that measurement because telescopes always have noise. And then passband, which indicates which filter was used. LSST has 6 filters from ultraviolet to infrared, and different filters reveal different aspects of the object's physics, which is very important for my problem. And finally, the detected flag is value of 0 or 1, and it indicates whether the telescopes actually recorded a clear detection or just an upper limit. This helps distinguish real signals from background noise. And by combining all these features, we can train the model to recognize the unique light curve shapes for different astronomical events. There are 10 different classes in my dataset, including several types of supernovae, variable stars, AGN, and more exotic events like kilonovae and tidal disruption events. Here you can see a list of classes alongside their distribution in the dataset. First graph referred to training set, and second to testing set. And I split all data into 80% training and 20% testing, while keeping the class proportion consistent, which is very important for evolution of my model. And as you can see, this data set is kind of challenging. It's real life data set, and many classes are imbalanced. For example, some supernova types are very common, while rare events like kilonovae are represented by only a few examples. And before testing the models, I had to pre-process the data. The numerical features were normalized to put them on the same scale, which really helps the neural network to learn better. And observations with missing values were removed, and target labels were encoded into numbers and converted to categorical format for multi-class classification. And also in that data set, from the start, there was 4 really underrepresented classes. There was only from 3 to 10 observations, and it was impossible to form a light curve. So I removed because it's kind of damaged process of learning of my model. Once I had the data set ready, the next step was to prepare it for training and test different models. I tested 3 different deep learning architectures, dense neural network, which is served as a baseline. Then I test an LSTM network, which designed to capture temporal dependencies in the light curves, and CNN, which can extract local patterns in the data. And to find the most effective model, I didn't just try one set of parameters. I used methods that called grid search CV with cross-validation, which basically systematically tests different hyperparameters combinations. For example, I varied the numbers of layers, numbers of neurons in each layer, learning rate and dropout rates, and grid search CV helped me to ensure that the final model configuration achieves the highest possible accuracy on unseen data. For training, I used Adam optimizer with categorical cross-entropy loss, and to avoid overfitting, which means that it will fit exactly to my data, but if I will try to run it on another, it would work much worse. And I tried to prevent overfitting, which was kind of difficult. I applied dropout, which switch off several neurons, and I used early stopping based on validation loss, which was very benefiting our models. And to measure performance, I looked not only on accuracy, but also precision, recall, and F1 score, since the dataset is imbalanced. And let's talk what I get. First of all, I checked how models working separately, which means first of all, I used only CNN model and didn't combine like CNN and LSTM. And also I choose better hyperparameters by using grid search CV. And is the result that I get that CNN, which recognize patterns on a little time period, works better than was dense, and LSTM which was very difficult to work with. And as I understand, it's because the real life data is too noisy and LSTM can't recognize patterns because of it. So my best model is CNN and dense combined. It has three convid layers with increasing filter size, which means that model become more complicated and complicated, and each followed by batch normalization and dropout, which is basically preventing overfitting. And after convolutional layers, global max pooling, that reduce the output to a fixed length vector, which then pass through a dense layer, and finally the softmax output layers for 10 classes. I trained model with Adam Optimizer, error stopping, and also I used a learning rate scheduler, that is method that variate learning rate by looking how model is learning, which has really helped in my situation. And CNN and dance achieves the highest accuracy of 75%, outperforming another architectures. And it shows that it can effectively classify astronomical objects using their light curves. And in conclusion, my study demonstrates that CNN and DANCE are most effective model for automated astronomical object classification. The CNN and DANCE outperformed all different other architectures, achieving the highest accuracy and reliably identifying patterns across multiple passbands. This shows that deep learning actually can process large data sets quickly, reduce human error, and detect subtle features that might be missed by traditional methods. However, some challenges still remain. Rare events like Kilinovae are harder to classify due to their limited examples, and noise in observations can lead to occasional misclassifications. And for future work, I would love to expand classes and improve detection of rare and noisy events, helping astronomers discover and study transit phenomena more efficiently. Thank you for your attention.
Well, Anastasia, that was a very interesting and exciting presentation. Thank you so much for sharing it with us. Questions from the audience or other panelists? All right. While others are thinking about their questions, I have a number of questions. The first one is, you mentioned that you had to like do pre-processing of data, like removing the undefined ones. You call them nans. Can you say more why that's important?
You're asking why I removed several classes?
Sorry, could you repeat that?
You ask why I removed several classes?
Yes, you mentioned that you had to do some data cleaning, right? To
Oh,
remove
yeah,
undefined values.
of course, because it is real life data, and it's usually very noisy, and it will be very difficult for a model to identify some patterns in that noisy data. And I need to put it on same scale because it was like starting from different numbers. And if we will scale in and putting on one scale, it will be much easier to identify some patterns, local patterns, and even big patterns for a model.
And the follow-up question, you mentioned the three different models that you experimented with. How did you pick those three? I assume there are even more than three to choose from.
I tested all deep learning methods, most popular methods. I also checked like LSTM bidirectional and others, but they performed really bad, and I didn't include it to my research. And also, I tried usual machine learning because all these methods that I was talking about is a deep learning. Um, and actually, traditionally, as I know, astronomers is currently using machine learning, and it but they use in like on local patterns, and that means that they are not and identify what object it is by themselves. They just help astronomers, and I used to I used deep learning because machine learning is already used, and I wanted to like make something new and try something unusual.
Sounds great. Well, Anastasia, there's a question from the audience. How did you select this topic of research?
Well, I was always fascinated by astrophysics, and I was wondering what can make by myself, not only to something that will inspire me, but also something that will contribute to real world. And as AI is now very helpful tool, I thought about that I can apply it to my research, and that's why I chose this topic.
Super cool. All right. So, final question for you. What was the most challenging part of this project?
I would say that build a model because I'm not really a programmer. I'm not a coder. And I have never built a model before, and I started to learning about deep learning from the scratch. And I wanted not only just write code, copy from internet. I wanted to understand how it works to make more the best model I can. Um, yeah, it was the most challenging part.
Got it. Well, Anastasia, thank you so much for that insightful presentation. And it's obvious that you've done some very remarkable work, given that you say you started from scratch. Hard to believe it. So congrats.